about this beautiful picture that you see over there about mole. This is only a mascot of mole. Mole is the unit of measurement, the base unit in the international system of units for amount of a substance, and a SI base quantity proportional to the number of elementary entities of a substance. So when you talk about mole, it's the same thing if I tells you I bought a ream of paper. So you know that ream stands for 500. So if I buy a ream of paper, I have 500 sheets of paper over there, right? And if I buy a dozen eggs, I know that dozen stands for 12. So it doesn't matter if I buy dozen donuts, will be 12. So that is the name you give. Ream, dozen, okay, pair, you know that is 2. And then came Avogadro number, which is the number of atoms and 12.01 grams of carbon. Avogadro was a scientist that came with the idea, with the theory that he could counting the number of atoms in 1 mole of any substance, and he came with and he tried to prove that 1 mole of any substance or any atom contains 6.02 times 10 power 23rd. Can be atoms, can be units, molecules, ions. Okay, so but unfortunately, all the scientists and the scientific board was like thinking that, okay, this scientist Avogadro is crazy. He cannot actually count and come up with this number. But after the time passed and they could prove actually the 12.01 grams of carbon really has 6.02 times 10 to the 23rd carbon atoms. Unfortunately, this was after he passed away, but they gave this the name of Avogadro to celebrate him. So the mole is a unit, as I said before, of measure for an amount of chemical substance. A mole, as I said before, is 6.02 times 10^23 particles. So you know already that 1 mole of any substance contains 6.02 times 10^23 units. This is very important, and as mole is, I always say, that is the start unit of chemistry, okay? Because you're gonna see that, as you saw before, that 1 mole of carbon contains 12.01 grams. So, but if I talk about 1 mole of water will contain 18 grams per mole. So see, the mass will change, but we're talking about 1 mole. It's easy to talk about 1 mole because that will be always 1 mole. But the mass will change because we change the substance, we change the element, okay? And we're gonna use this, that you know already, the Avogadro number, as unit factor. We're gonna apply the unit analysis method. So let's go to example over here. So here asking how many sodium atoms are in 0.240 moles of sodium. So you know that 1 mole of any substance is 6.02 times 10^23 whatever unit. Here it's atoms, so we can use atoms over here. Or you can say that 6.02 10^23 atoms is contained in 1 mole of any substance. So the unit factor that you're going to use here is this, because atoms is over here, so it's the periodics up there, and the mole it's up here, is down here, so we can cut off. So you need always to work with the units, okay? This is not about memorization, Of course, you need to memorize and then know that 1 mole is 6.02 times 10 power 23rd atoms. However, how to use your unit factor is depends of the units you have here, the unit they asking for. So you have over here the given value, and then you have the unit factor. So I can cut off moles per mole. So I'm gonna multiply this, and I'm gonna have 1.44 times 10 to 23rd atom of sodium. If you do opposite, you're gonna have mole sodium times mole sodium. Look at this, and here will be atoms. So then if you multiply over here, will be mole square sodium plus divide by atoms. That is not the unit you want. So work with the units, because that will help you to know if you're doing the right thing. Okay? So I suggest to you to pause your video and try by yourself this problem. How many moles of aluminum are in 3.42 times 10 power 24th atoms of aluminum? So again, you need to use the unit factor. So here I'm going to use this unit factor because I know what I want is moles. So moles must be up here. So I will multiply the number of atoms that I know by this unit factor, and I will have, I will have the moles of aluminum. Okay? And before I make the calculations, I already know that will be smaller than 1 mole. Because if your 1 mole is 6.02 times 10 power 23rd, of course 10 power 21st will be smaller number of moles, right? So that is another way to check if you are doing the right thing. And then we have the molar mass. So the molar mass, the atomic mass of any substance expressed in grams, is the molar mass of that substance. The atomic mass of carbon is 12.01 atomic mass unit. Therefore, the molar mass of carbon is 12.01 grams per mole. Since nitrogen occurs naturally as a diatomic, so the molar mass will be 2 times the molar mass, the atomic mass of the nitrogen, which is 14.01 grams. Where do you get these values? In the periodic table, right? So in the periodic table, you're going to see there the nitrogen. So we're going to see something like that. So we have here 7, and then we have the molar mass over here. Okay? So some will come with the 5 significant figures, some will come with the 4 significant figures. It depends on the periodic table that you have in hand. Okay? And as I said before, mole is a mole. Doesn't matter if I'm talking about 1 mole of water, 1 mole of CO2, 1 mole of sulfur dioxide. Will be always 1 mole, but the molar mass will be different. Here I have 1 mole of different compounds over here. So I have water, and I have carbon, and I have lead, I have coins over here, I have salts. So can you see the quantity? So if I'm talking about 1 mole for each substance, you see the quantity is different for each substance, each element. So when you work in chemistry, normally we're going to work with moles, because mass will vary when you have a different substance, okay, or different elements. And how are you going to calculate the molar mass? This is very important here, what I'm going to say. First, you need to read the things and practice nomenclature, because that will help you during the test. So I have here copper 2 nitrite. I could ask you to write the formula and then calculate the molar mass. So another thing is, when you write the formula, you need to know that when you use a parenthesis, like here, because you have a copper 2, right? Copper 2, and the nitrite over here is -1. So when you cross over here, you need to use parentheses for both to say that 2 will be 2 of NO2. That means NO2 plus NO2. So I have 2 nitrogens. 2 times 2 is 4 oxygen. And this makes all the difference when you calculate the molar mass. Okay, so I have the molar mass of copper, which is 63.55, plus 2 times the molar mass of NO2. So we have the molar mass of NO2 over here, 14.01, which is nitrogen, and 2 times of oxygen, with 16. Okay, in your periodic table it's 15.999. That's okay. As I said before, it depends on the periodic table that you have in your hands, or if you round or not the numbers. So now I'm gonna add all together, and I have 155.57 grams per mole. Okay, so pay attention on the parentheses and the atomic number and your periodic table and how to calculate. Now we're going to use the molar mass of compound to convert between grams of substance and moles or particle of substance. But remember, let me just choose another color over here. Mole is the start of the units in chemistry. So if I have atoms, molecules, or units, or ions, we know that we need to use the Avogadro, that you know that is 6.02 times 10 power to 23rd particles to find moles. And then if I want to find grams mass, I'm going to use molar mass. And of course you can do like the same, the opposite way. Like if you have grams, I can find moles, and if you have moles, I can find atoms. But we cannot never go directly here, atoms to grams, because atoms, 1 mole is 6.02 times 10 23rd particles, or atoms, but not moles. See, so you have to pass all the steps before you get to the moles. Okay, moles first, then you get atoms. Mole first, then you get grams. Okay, so what is the mass? See, the question here is the mass, grams, right? And remember, mole is our star over here. So if you have moles and want to find grams, we're going to use molar mass to find out, because molar mass is grams per mole. So I have a number of moles, and titanium, the atomic mass unit, is just look at the periodic table, and you're going to find there 47.88 grams. So using the molar mass as the unit factor, I'm going to put moles down here because I want to cut off moles, because what I want is grams. So then I have 63.7 grams of titanium, because I multiply 1.33 times 47.88. Okay? I encourage you to pause your video and try by yourself. What is the mass of 2.55 times 10 power 23rd atoms of lead? So the first thing that you need is, okay, so I know the mole is the star in chemistry. And I know to find mass, I would need molar mass. But they're asking me mass, and they are giving me atoms. So if I have atoms over here, I need to use Avogadro, because I know Avogadro, it's 1 mole is equal 6.022 times 10 power 23rd atoms, right? So here will be our first step over here. So I'm getting the highlight over here. So that is our first step. Convert these atoms to moles, and then we go to moles to grams using molar mass. Okay, so try by yourself. Stop your video. So I have the first step over here, as I said. Oh, I'm sorry, I want the highlighter over here, and I can't find. Okay, so I have the first step over here. See, 1 mole, it's equals 6.02 times 10 23rd. So I'm cutting off atoms and atoms. And then if I have moles, because I'm going to multiply this by 1, divide by 6.02 times 10 23rd. And then I'm going to find moles. So if I multiply direct by 22 207.2 grams because it's smaller mass, and 1 mole I have this, I'm gonna find the grams of lead in that case. Okay, it's all about this: moles to grams, atoms to moles. Okay, again, here we have how many fluorine molecules are present. 2.25 grams of fluorine gas. Oh, okay, so now I have molecules. No, I want molecules, and I have grams. How am I gonna do? Remember, just always gotta use it to write down. Okay, so I have moles. Let me grab my pen over here. I have moles is my stars, and if I have molecules or atoms or anything, I will need what? Avogadro. And if I want grams, I will need molar mass. But now it's opposite. So I have grams and I want molecules. So I need to go in this way. I'm going to use molar mass to find the moles, and then I use Avogadro to find the molecules. Okay? So get the molar mass of fluorine. So it's 2 times 16, and you're going to have a 38. Sorry. Is 19 grams per mole, because it's 18,998 grams per mole in your periodic table. So if you multiply by 2, you're going to have 38 grams per mole. Okay, this is what I have over here. That is molar mass, 38 grams per mole. So now this is the first step over here, remember? So I'm converting grams to moles. And then I go to the second step, which is over here. So I'm using Avogadro over here to find molecules. So now my result is 3.56 times 10 power 22nd molecules. Good? Easy. One more, just to practice. What is the mass of single molecule of sulfur dioxide? See the way that I'm asking you? I want to know grams per molecule. Okay, so I need the molar mass. So molar mass of SO2 is 64.07 grams. So how I did that? I went to periodic table and I look for, let me just change this. Okay, and in my periodic table I found sulfur, which is 32 grams, more or less 32.006 grams per mole. And then I have oxygen, which is 15.999. So I have a 2, so it will be 2 times this. And then you add all together and you have 64.07 grams per mole. If you don't know how to do molar mass, so practice a little bit, because that will help you and everything. This is the key to go well in the stoichiometry problems, okay? So we want mass to molecules, per molecules. I'm going to use Avogadro. I have moles. And I know that 1 mole is 6.02 times 10 23rd molecules. So what I'm going to do is dividing, because I can cut off moles, see, over here, and I'm going to have molecules. So it will be 64.07 divided by 6.02 times 10 power 23rd molecules, and I'm going to have my number of grams per molecule. Okay? Another very important thing here is molar volume. Molar volume tells us that 1 mole of any gas in a standard temperature and pressure, which is 0 degrees Celsius and 1 atm, occupies 22.4 liters. Doesn't matter if I'm talking about CO2 or nitrogen or SO2 or water vapor, doesn't matter. Any gas in STP conditions will have this, occupies 22.4 liters. Okay, so but it must be right STP. Like here in this box, doesn't matter the gas we have here, 1 mole of any gas will occupy 22.4 liters. So now you know that 1 mole of gas, we have 6.02 times 10 23rd molecules of gas, and that occupies 22.4 liters of gas. And if you look here, I have that 1 mole of any gas that you see over here. Let me just grab here my highlight. The number of molecules will be the same, 6.02 times 10 to the 23rd. That is Avogadro numbers. The molar mass, so the mass will change as we talked before, always, but the molar volume will be the same for all. Will occupy 22.4 liter per mole in STP conditions. Okay? And with this, we can also calculate the density of the gas. So the density of a gas is much less than the liquids. We can easily calculate the density of any gas if you already know that 1 mole of any gas in STP conditions occupies 22.4 liter. Just divide the molar mass by the molar volume in liters. So if you have a molar mass of something and you know that molar volume is 22.4 liters, it's easy to calculate the density, like in here in this example. So if I have to calculate here the density of methane gas, methane is carbon and 4 hydrogen. So you go to periodic table and you're going to have the carbon is around 12 plus 4, which is times 1 because it's 1 grams per mole, close it. So I'm rounding, will be 16 grams per mole. Here I have 16.05. It's depending on how you round the numbers over here. Normally we don't round the numbers before you finish or calculate. Okay, that is the rule. You don't round the numbers before you finish all the calculations. But here I was only rounding just to show you how to calculate. So we have 1 carbon, so you go to the table and we're looking for the numbers, the atomic number, and the hydrogens 4 times the atomic number of hydrogen, then add it together. So I have the molar mass. And I know the molar volume is 22.4 liters per mole because they told us it's STP condition. So divide the molar mass by the volume, the molar volume, so we cut off the moles, and you're gonna have the density easily. Okay? Good? Okay, so let's keep going. So like here, if you have an unknown gas which 4.29 grams occupies 1.50 liters at STP, what is the molar mass? So they want grams per mole, right? And we have grams per liter. This divided by this will give me density, grams per liter. So I want grams per mole. How are we going to do that? So I know that 1 mole occupies 22.4 liters. That I'm using as a unit factor. What we already know. So I have a grams per liter. I'm going to cut off liters. So 4.29 times 22.4 divided by 1.50. We have 64.1 grams per mole. We now have 3 interpretations for mole. So we know that 1 mole is 6.02 times 10 to the 23rd particles. And also we know the molar mass, which is grams per mole. And 1 mole of any gas in the STP conditions occupy 22.4 liters. That is the molar volume. So this gives us 3 unit factors to use to convert among the moles, particles, mass, and volume, which is very important to use when you're calculating using stoichiometry calculations. Okay, a sample of methane CH4 occupies 4.50 liters at STP. How many moles are present? Okay, they're asking moles. I know the molar volume, which is 1 mole, is equal to 22.4 liters. And I have liters. So if I use 1 mole is 22.4 liters, and I multiply by liters, so I'm going to cut here. What are you going to have at the end? Moles. So I only did this. So I will divide by 22.4 liters, so I can cut off liters, and they're going to have a number of moles. 0.201 moles of methane. Pause your video and try by yourself. what is the mass of 3.36 liters of ozone gas at STP conditions? So I want a mass. So what are you going to need here? So we want the mass and we have volume. But I know that 1 mole occupies 22.4 liters, so I can find moles, right? So if I use the volume, the molar volume, and then I use the molar mass, look at this is molar mass, I'm gonna find grams. Okay, first you convert to moles and then you convert to grams. So we have volume, you convert to moles, and then you find grams. How we convert volume to mole? Using molar volume. How you convert moles to grams? Using molar mass. Okay, good? Okay, so let's calculate how many molecules of argon gas occupies 0.430 liters at STP. Okay, again, I know that 1 mole occupies 22.4 liters in STP conditions. And they ask me molecules. Okay, so I have volume. So I can use the molar volume, right, to find moles. And I can use Avogadro, right, to find molecules. Good. So first I use molar volume, and then I'm going to find moles. And then I'm going to use Avogadro, because I'm going to cut over here, and I'm going to find molecules. Easy. So molecules, atoms will be always a large number, like you see over here, or very small numbers. Another very important thing in chemistry is percent composition and everything. So if I go in the supermarket and I buy a cup of yogurt, I'm going to read how many percent of sugar we have over here, or percent of fat. So, and the percent composition is very important in whole chemistry. Not only you buy a food and you need to control the sugar contents in your food. It's important in everything that we do in chemistry. So the percent composition of compound lists the mass percent of each element. So it will be always a part over the total multiplied by 100. Like here, we have water, and says that we have 11% hydrogen and 89% of oxygen. And water, we have 2 atoms of hydrogen and 1 atom of oxygen. So to calculate this, what you need first is assume 1 mole of compound. So I have 2 moles of hydrogen and 1 mole of oxygen. So, and then I will calculate the mass, the total mass of water molecule. So I have 2 times 1, that is the atomic mass unit that you find in your periodic table. Here the atomic mass, so we have 1, and here I have 2. So we have 18 grams of water and 1 mole. So now, if I have the mass of hydrogen, which is 2.02 grams, that is the total mass of hydrogen, and 16 grams is the total mass of oxygen. So that is the part of oxygen, this is the part of hydrogen in this total. So what I'm going to do is the part, see here, divide by the total, multiply by 100. And you're going to have the percentage of each element. Doesn't matter the size of the molecule, you could do for sulfuric acid, for example. So we're going to do the same thing. You're going to calculate the molar mass, and then you get the part of hydrogen, part of sulfur, and part of oxygen, and divide by the total. So let's do this one. Toluene is a white crystalline substance that explodes at 240 Celsius degree. And here you have the formula. So remember, pay attention that this 3 multiplied by all the elements. So I have 3 times, so I have 3 atoms of nitrogen, and 3 times 2 is 6, 6 times it will be 6 atoms of oxygen. Okay, so you're going to calculate your molar mass, which is 240 27.15 grams of TNT. So now what I'm going to do is divide the part of carbon divided by the total, and then multiply by 100. I have the percentage. I'm going to do the same thing with hydrogen, nitrogen, and oxygen separately, like here. So I'm getting the part, as I said before, divide by the total, multiply by 100. And you get the percentage for each element in your molecule. And this takes us to another very important thing here, the empirical formula. The empirical formula of compound is the simplest whole number ratio of ions in a formula unit, or atoms of each element in a molecule. So the molecular formula for benzene is 6H6. I can divide to simplify by 6 each of those, and it will be 1 and 1. Or like here, I can divide by 2 here and 2 here, and they're going to have 4 and 9. That is the smallest whole number ratios for each atom over here in this formula. Look at here. We do have a problem. If you don't know how to use empirical formula, that will take you to make really hard mistakes. Look at this. The empirical formula CH can be for acetylene or benzene, because here I could divide by 2 or 6 over here, but look, we are talking about different substances that have a very different boiling point. Look at this over here, CH2. So I could be the empirical formula for butene, ethylene, cyclohexane. So because if I divide here by 2 or here by 4 or here by 6, all the elements, right? So we have to divide by the atoms over here. So we're gonna have this as empirical form, but they are different substances and with very different boiling point. The same thing happens over here. So how are we going to know how to work with the empirical formula? Actually, we can calculate the empirical formula of a compound from its composition data. We can determine the mole ratio of each element from the mass to determine the empirical formula, for example, of radium oxide. If it tells you that 1.640 grams samples of radium metal was heated to produce 1.755 grams of radium oxide. Okay, this is a reaction that we are adding oxygen over here. That means if I had before only 1.6040 grams, now the difference between those two, the initial and the final mass, is actually the quantity of oxygen. So I have the oxygen over here and I have the radium over here. So now, after you calculate the molar mass, so the molar mass of radium and the molar mass of oxygen, so you don't actually calculate, you just go in your periodic table and look for the elements and look for, because now I need the mole of radium. So if I divide by the mass, because I know that there's a smaller mass, so we're gonna have moles. If I have grams, if I want a moles, I use molar mass, right? Of each element, not the total. Remember, we are not calculating percent composition here. We are calculating empirical formula. So we're going to do element by element. So the molar mass of each element. So we're going to find number of moles of radium. And you're going to do the same thing of oxygen. Now, the second step will be looking for those numbers and see which one is the smallest one. As this, right? So we're going to divide both by the same number, 0.0079. As soon as you divide, to simplify, you're going to have 1 and 1. So radial O is the empirical formula. Okay? Okay, so we can use percent composition data to calculate empirical formula as well. So when you have percent composition, what you're going to do is you have to assume that you have 100 grams. So 92.2% in 100 grams means that I have 92.2 grams of carbon and 7.83 grams of hydrogen. And that's simple. Okay? So what are you going to do now? So first, you're going to calculate the moles of each element. So remember, to calculate the moles, and if you have grams, I need molar mass of each element. So I have here 12 grams per mole. I'm using as unit factor. Moles is up here because I need moles. And I can cut off grams with grams. And I find the moles of carbon. The same thing you're going to do with the hydrogen. Now the second step is, you're right, we're going to choose the smallest one and you're going to divide both by 7.68, like here. So now we're going to have CH. CH is the smallest number to get the whole formula over here. So that is the empirical formula. Okay? So the empirical formula of acetylene is CH. This represents the ratio of carbon to hydrogen atoms on acetylene. The actual molecular formula is some multiple of the empirical formula. And how are we going to do this? How are we going to find the molecular formula? So it's not hard. If it tells you the molecular the molar mass of molecular formula is 26 grams per mole, and you know how to calculate the molar mass of this carbon and hydrogen, that is the empirical formula, you're going to divide both, and you're going to have the 2. So 2, so you're going to substitute over here, so it'll be 2 carbons and 2 hydrogen. That is the molecular formula. So let's do one more. So the percent compound was found to be 63.5, right? Percent of silver. And then I have 8.2% of nitrogen and 28.3% of oxygen. So first thing that we're going to do is find moles. Remember? Find moles. So, and actually the first thing is take in consideration that we have 100 grams sample. So let's assume that. So then we have 60.3 grams. So let's put it like this. So I have silver, and I have nitrogen, and I have oxygen. So silver is 63.5 grams. I have nitrogen 8.2 grams, and I have oxygen 28.3 grams, right? So now what I need is to find the molar mass of each one. So I go to periodic table. Molar mass is grams per mole, okay? So what I have here is, if I go to periodic table, I'm gonna find 107.868 grams per mole. And nitrogen is 14.007. And the oxygen is 15.999. Okay. So here is grams per mole. What I want is moles, right? Moles. So to find the moles, what I need, if I have grams, remember, I need the molar mass. But I need the grams over here and the moles over here. So if you have a 63.5 grams, I have 1 mole of silver. I have 107.868. Oh, let me erase this because that's some messy. Okay. Oh, I grab the ink again. Nope. Sorry. So 107.868 grams of silver. So I can cut grams with grams, and I'm gonna have moles. So I'm gonna use my calculator over here. I'm sorry. I need to calculate. You can do the same on the other side. So if you calculate, will be 63.5 divided by 107.868. So I have 0.589. And we're going to do the same thing here. 8.2 divided by 14.007, and they're going to have 0.585. And they're going to do this, 28.3 grams divided by 15.999 grams, and I'm going to have 1.769. So now we're going to choose the smallest number over here, which is this, right? So we're going to divide everybody by this. Here, the same thing. And here, the same thing. Okay, so now we're going to have 1.01. And here it's 1, right? I'm using 3 significant figures because this is 3 significant figures, that's right. And then I have here this divided by this, which give me 3.02. So now you can round because we're in whole number. So it will be silver, nitrogen 1. So we don't write down the 1. So I have a 3 over here. So that's my formula. Okay. So, and all the units you have the summer over here. So we have an Avogadro number. You already know 6.02 times 10 power 23rd. And this is 1 mole of any substance contains this quantity of atoms, molecules, units, whatever unit you use over here, right? So let me just change my color over here because this I cannot see. Good. So could be atoms, molecules, right? Particles, unit. So the molar mass of substance is grams per mole. So it's the atomic mass of each element in the formula. So you put it all together. Just remember when you have a parenthesis like NO3, for example, 2, so we need to multiply each element by 2. At STP conditions, 0 degrees Celsius and 1 atm, we know that 1 mole of any gas occupies 22.4 liters. When you convert between the number of particles and the moles of a substance using Avogadro number, because we're going to use that as unit factor. If you want a mole going to be up there. If you want particles or molecules must be up here, so it will be Avogadro number over here and the mole down here. We can convert between molar mass of substance and the moles of substance using molar mass. So just remember, if you have a volume, you can use the molar volume that you already know, which is 22.4 liters in 1 mole of any substance, any gas, in STP conditions. And then we can find mole. Also, if you have Avogadro, if you have molecules, particles, atoms, you're gonna use Avogadro to find moles as well. And through moles, I can use molar mass to find mass. You can find grams. And you can do in this and the other way as well. Okay? So just pay attention to the units and the concepts that you just learned. So the percent composition of a substance is the mass percent of each element in the substance. So remember, it's part divide by the total multiplied by 100. And the empirical formula of substance is the simplest whole number ratio of the elements in the formula. You can find out through the percent that you have. So we just needed to assume that you have a 100 grams sample, and then you find the number of moles, and you're going to find the empirical formula. And the molecular formula, you just need the molecular mass, the molar mass of the molecular formula, divide the molar mass of empirical formula, and you're going to have the ratio. So we're going to have a CH, and that's N. We'll multiply each one. If N is equal to, we're going to have a C2H2, for example. Okay, easy. Okay, that's it. That's all. Bye for now.